So I said previously that the average atomic mass that's on the periodic table is different from the mass number we discussed. So remember, the mass number is simply the number of protons plus the number of neutrons, whereas the average atomic mass is the average of the masses of all the naturally occurring isotopes. So before we do calculations involving average atomic mass, let's look at a calculation we're more familiar with. Let's look at calculating a grade in a class where the categories of grades have different weights. So we'll calculate your weighted average in the class. And that's how we calculate the average atomic mass. It's a weighted average rather than just a simple average. So let's go through this calculation, and then hopefully when we do the calculations with average atomic mass, it'll make a little bit more sense to you. So we have a class where test grades are 70% of your grade, homework grades are 15%, and lab grades are 15%. And you want to calculate your overall average in the class. So just by looking at this, you can probably realize that your homework grade really won't affect your overall average as much as your test grades, because it's only worth 15% of your total grade. So the first thing we need to do is go ahead and get your average for each of the categories. So let's go ahead and get your test average for the class. So we can do 92 plus 83 plus 88. So I get, you had 263 out of the 300 possible test points in the class. So your average, if I did 263 divided by 300, okay, times 100, and for the sake of simplicity, we'll just round these off to the nearest whole number. So you have an 88 test average. So then let's look at your homework averages. So for your homework, you scored a 10, a 17, a 22, a 5, and a 7. So you got 61 points out of a possible 30, 40, 50, 60, 70 points. So your homework average is 87. Okay, so that's your homework average. And then let's look at your lab grades. You got 25 plus 30 plus 18. So you got a total of 73 points out of 90 points possible. So your lab average was 81. Okay. So now you have your test grade, your homework grade, and your lab grade, and you want to find your overall class average. So your class average will be equal to your 88 test average times 70% converted to a decimal. So to take a decimal to percent, you divide by 100. So times 0.7 plus your homework average, which is 87, times 0.15 plus your lab average, which was 81, times 0.15. Okay. So if you set that up, go ahead and type that in your calculator. Okay, so when you type that in, you should get 86.8, and if we round off to our original, we'll just keep it to the nearest whole number. You have a final class average of 87. So notice if you go back up here and look at what that means, your test average was 88, but your lab average was an 81. So if we just did a simple average of these three numbers, 88 plus 87 plus 81, your average will be an 85 in the class. Okay, so simple average, just add them all together, dividing by 3. But instead we calculated it with a weighted average, because we said the tests are more important. They mean more, so they carry more weight. Therefore, they should affect your final average more. So we use the same concept when we calculate average atomic mass. And we determine which categories are most important by which ones occur most commonly in nature. So let's look at boron, for example. the two common isotopes of boron are boron 10 and boron 11. So approximately 20% of boron is boron 10. Approximately 11% of boron is boron 11. So just by looking at this, if we did a simple average, the average atomic mass would be 10.5. We can do that pretty simply. But if you look at these abundances, so we'll label that, we see that the mass of 11 should be more important. It should carry more weight. So another way of thinking about that is if you were able to grab a single boron atom somehow, you have an 80% chance of grabbing a boron 11. And you have a 20% chance of grabbing a boron 10. So sometimes you can see the average atomic mass formula written like this. So we'll just have capital M for average atomic mass equals the sum of the individual masses times the abundance. Little m stands for the mass number, and P stands for the relative abundance, and the sigma tells us to add it all together. If that doesn't mean anything to you, that's perfectly fine. Don't worry about it. We'll break the formula down and just look at how to do it. So in this case, I have these two abundances, and I want to calculate the average atomic mass. So we'll just say atomic mass equals the mass of the first isotope, 10 times 0.2, plus the mass of the second isotope, 11 times 0.8. So when you plug that in, you should get something like 10.8. Okay, so that is our average atomic mass for boron. If you look at the periodic table, you'll probably see something like 10.81, which is not quite what we calculated. So why do we have that difference? Well, think about how difficult it would be to estimate these average abundances for all the boron on the entire Earth. A lot of times you'll actually see different atomic masses listed because they arose from using different abundances based on what type of rock or what type of mineral that atom was present in. So a lot of times on some continents you might have a certain isotope of an element that's very common in a certain type of rock, but on a different continent you might have a different isotope that's far more common. So that's why the atomic masses sometimes vary, because these abundances are very difficult to calculate. So now let's go ahead and take a look at sulfur. Okay, so I listed out the 4 common isotopes for sulfur as well as their relative abundances in nature. And I want to calculate the average atomic mass. But notice there's a little bit of an issue here. I don't know the relative abundance for sulfur 36. But I know that the abundances always have to add up to equal 100%. So I can pretty easily subtract all the percentages from 100 and find that the abundance of sulfur 36 is 0.01%. So you see that sulfur 36 will probably have a very small impact on the overall average atomic mass. So just by looking at these numbers and these abundances, we can see that the vast majority of sulfur on this Earth is sulfur 32. So we could go ahead and estimate that the average atomic mass of sulfur will be closer to 32. So let's go ahead and do the math here. So we can say that the mass of sulfur 32 times 0.9499. Don't forget to convert that percentage to a decimal or you'll get a very large number. It's not easy to forget to do it on numbers like this, but on a problem like this where you have 33 times is 0.75%, it's very easy to go ahead and just write 0.75. But don't forget you have to divide that by 100, so it's 0.0075. Then we have 34. So we go ahead and convert that to a decimal, so 0.0425. And then the last one, I have 36 times 0.0001. Okay. So I go ahead and do all those operations, and then I add them together in my calculator. You should get 32.09. And again, that's going to differ slightly from the number you see on the periodic table for a variety of reasons. Notice there are a couple of isotopes of sulfur we didn't list here, like sulfur 35, which does exist, but it undergoes radioactive decay very quickly, so we don't include it in the calculation here. So we can list this with 2 decimal places, which is the standard convention for atomic masses. We typically don't use significant digits in atomic masses. We round those to 2 decimal places. So now we have the formula and the tools to be able to calculate the average atomic mass we see on the periodic table. And also, with the formulas that we've used, if I were to give you, let's go back to the class average example. If I gave you your class average, you knew the weights for each category, and one of these grades were missing, could you use simple algebra to solve for that grade? Yes. And down here you could do the same thing. If you knew the average atomic mass for boron, but one of the masses or one of the abundances were missing, you could very easily find one of those. So let's go back and review really quickly the 2 major concepts. So we have mass number. So mass number is not on the periodic table. So let's make a little chart. Not on table. It is a whole number, and it refers to a single atom. Okay, and it is just the number of protons plus the number of neutrons. But then we have the atomic mass, or you'll see it written as average atomic mass quite often. It is on the periodic table. Abbreviated periodic T. It is rounded to 2 decimal places when we do calculations. And so that's something, there are many more decimal places present often, but we round to 2 decimal places for our calculations. And it is the weighted average of often many isotopes. It does not refer to a single atom. So we use average atomic mass the majority of the time because we typically don't deal with single atoms that often. We're more concerned with the overall average of a large sample of atoms. So hopefully that clears up any confusion you have on the 2 topics, and we can go ahead and move forward. Let me say one last thing before I end the video. Notice for all the calculations we've performed so far, we have used the isotope masses as being nice round whole numbers. Oftentimes when we do calculations, we won't use these simplified rounded numbers. So just be aware when you see calculations involving, they'll call it the exact weight or the exact mass. And that takes into consideration a lot of things other than just simply the number of protons and number of neutrons, but it changes the calculation in no way. So for example, if this isotope of sulfur has a mass number of 32, but a true mass of 32.0012, for example, we would simply just plug in 32.0012 in the calculation, so nothing would change at all there.